The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
A small object of mass m starts from rest at the position shown and slides along the frictionless loop-the-loop track of radius r. What is the smallest value of y such that the object will slide without losing contact with the track? So give us a situation. We have a track goes into a loop-the-loop, radius r. We have our object of mass m, and it is going to be at a height y above the top of the loop. They want to know what y is, and it's going to be in terms of r with all our answers. So, to start off this problem, we know it's going to be an energy problem, because pretty much anytime you have something where you have a height that's turning into a velocity, or you're trying to calculate a velocity based on a height, or any relationship between those two, energy is always a good approach. So, looking at our energy, what we can do is we can say our potential, I'm going to set our datum, or where our potential energy is equal to 0, right here at the line, the bottom, the top of the loop basically. So right there, I'm going to say, if you're there, you have no potential energy. So initially, we know it starts from rest, so it has no kinetic energy. If there's no springs in any part of the problem, there's no external forces outside of gravity, so we don't have to worry about any work or friction or anything like that. So basically right here, all it has is potential energy. So we say our energy initial is equal to our energy final, and we can say that our potential energy, or mgy, y, our height, right there, is going to be equal to, now the second point we're going to be looking at is right at the top of the loop. Now at the top of the loop, it has no potential because it's at the location, the height, where we said there is no potential energy. It's moving, so it has kinetic energy, and there's nothing else going on, so mgy is equal to 1/2 mv squared. And we can cancel our m's, and we're left with gy equals 1/2 v squared. Okay. Now what we're looking for is y, so we can rearrange it and say y is going to be equal to v squared over 2g, which is not the format of any of the answers given to us. So we know we need to do something else to find out some more information, preferably figure out a way to get rid of this v squared and this g. So, what we can do is anytime you have something moving in circular motion, and you know information about that, especially like the radius, which all our answers are in terms of the radius, you can use your centripetal forces equation, which is just the force equation, F equals ma. So we can say the sum of our centripetal forces is equal to our mass times our centripetal acceleration. Okay? So at the top of the loop, let me draw this, forces acting on this object would be mg and our normal force. And don't forget, at the top of the loop, the normal force points down. At the bottom of the loop, it points up. It's what's holding it inside the loop. So the normal force is actually always going to point inwards. And gravity, of course, always points downwards. However, specifically in the problem, they state, what is the smallest value of y such that the object will slide up without losing contact with the track? The smallest value without losing contact. So what they're trying to say there is, it's just barely staying on the track. So whenever they have a situation like that, what they're wanting you to realize is, if it's about to fall off, the breaking point would, if it is falling off, then there's no normal force due to the track. The only force acting on the object would be the force of gravity. So if it isn't falling off, there would be a normal force. So the breaking point right there would be basically the point where the normal force is actually just equal to 0. Okay? So what we're going to do is assume our normal force is equal to 0 right when it's about to fall off. So our sum of our centripetal forces, mg, would be our only centripetal force. Now, as far as your positive and your negative with your forces, you can do whatever you'd like. You can set up to be positive, you can set down to be positive. I generally like to call anything pointing radially inwards or just towards the center of the circle to be positive. But I know a lot of you guys like to call up positive, so let's just do that. So this is pointing downwards, would be negative. Now on the right side of the equation, we have our mass times our centripetal acceleration. And we know the formula for that is going to be v squared over r. And our acceleration vector at the top of the circle points downwards. Acceleration vector for an object moving in the circle, the centripetal acceleration vector, always points radially inwards. So from wherever you're at towards the middle of the circle. So in this case, straight down. So this is also a negative term. Ends up just canceling itself out. No big deal. We can cancel out our m's, and now we're left with the equation g is equal to v squared over r. So we actually could solve for v squared if we knew what r was. Now what we're looking for is y. Y is not in this equation, but a lot of the terms over here are. So what we can do is just basically rearrange the equation however you see fit. I kind of like saying v squared is going to be equal to g times r. That way I can just plug in for v squared g times r. So we come over here, take this guy right there, plug it in there, and we end up with our equation y is going to be equal to gr over 2g, and our g's cancel, and we're left with our y is just going to be equal to r over 2, which is going to be our correct answer, choice number 1. So, the point of this is roller coaster problems in general are usually energy problems, at least at some point. Anytime you have height-velocity relationships they're asking for, energy is a good approach. If you can't do it with energy and you need something else, anytime you have something moving in a circle, you can always use Newton's law for centripetal motion. And yeah, that's the end of the problem.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.